Again, I also would like to thank the organizers for inviting me to speak in this very nice event. Um, what I'm going to present is the result of, I would say, 3 papers we worked on in the last couple of years. So we means myself with Amitabh Basu, which is who is in Johns Hopkins in Baltimore, and Michele, who is in Padua. He technically retired, but he only retired from teaching. He's still doing a lot of research. And Hongyi Yang, who was at the time he was a PhD student of Amitabh, and now I think he has a position as a postdoc in at Cornell University. So the idea is to try to see if from the theoretical point of view we can say something about the relative strength of the cutting plane approach and the branch and bound method for mixed integer optimization, and maybe trying to understand if there is a theoretical foundation for let's say for the superiority that the branch and cut seems to show when compared to just branch and bound or just the cutting plane approach. So let me immediately state our goals, because they're very, very easy to state. So I would say there are 2 main goals. So one is, as I said, to try to make a comparison from a theoretical point of view of the performance of a branch and bound cutting plane. And the other one is to see, to show that there are instances, there are situations, and what are these situations in which a branch and cut really outperform a branch and bound and cutting plane when they are considered as a algorithm that do not interact with each other. And I think the motivation for this kind of questions should be clear, because for the first question, the reason is that branch and bound cutting planes are, well, I wrote among just to stay on the safe side, but I would say they're really the main general purpose, at least, techniques for mixed integer optimization problems. But if you look into the literature, there's not much about the relative strength of one method compared to the other from the theoretical point of view. And as to the second goal, well, everybody is aware of the fact that in practice, at least generally speaking, of course, with all the exceptions that one can think of, but generally speaking, branch and cut is the winning algorithm. Usually just branch and bound and just cutting planes alone do not are not very, very effective and efficient. So I'm repeatedly saying the mixed integer optimization. So what do I mean? Well, the setting, our setting is the following. So this will look very abstract, but I will make things immediately more concrete. But this is the most general situation we can deal with. So we have some optimization problem in which we have a convex set C. So it's a convex optimization. And then you have some constraints which are not convex and impose, as I said, some non-convexity. Usually you have the condition that the variables are integer or some variables are integer, but you can also think of different non-convexity constraints, like, I don't know, complementarity of the variables, product of 2 variables equal to 0, or other things that are very common in practical problems. Here the objective function is linear, but it's a very standard trick to model every convex optimization problem with a linear function without loss of generality. The typical case one can keep in mind to have things more concrete in mind is with the case of mixed integer linear programming. In this case, the convex set C is just a polyhedron, and then the non-convexity is given by the integrality, or maybe requirement on all the variables or on some variables. So if, for instance, if you want integrality on all the variables, then you set this S to be just the set of integer points. Okay, so you can safely keep in mind the case of mixed integer programming, but most of the things that I will say work when you have a convex set, not just a polyhedron, and when you don't have integrality requirement, but a more general non-convex requirement. So I want to compare branch and bound and cutting plane. So branch and bound clearly is an algorithm that we all know, and is based on the notion of disjunction. So we apply some kind of disjunction to our set, and then we create 2 subproblems. Cutting plane is very, very vague, because there are many cutting plane paradigms. Of course, if we make a comparison, we should try to make the comparison in some sense fair. And so we decided to consider as a first step cutting planes that also, like the branch and bound, in some sense arise from the notion of disjunction. So let me clarify what I mean. So usually in branch and bound, you apply a disjunction on a single variable, so what I will call a variable disjunction. So you select a variable xi and you require that it is less than or equal to some integer or greater than or equal to the next integer. So geometrically, you have this kind of disjunction where the set D is the pink set, okay? And the important thing is that this set completely covers the integer points. Let's say that the non-convexity constraints are just the integrality requirements to make things more understandable. But at least in principle, even though probably nobody does that in branch and bound, you could also apply any other kind of split disjunction. So split disjunction is more general than variable disjunction. It means that you geometrically you take two parallel hyperplane and then you take the part which is not between them, where the hyperplanes are such that no integer point falls between the two hyperplanes. But algebraically, you just have an inequality ax less than or equal than b, or ax greater than or equal to b plus 1, where a and b are both integer vectors and number. In principle, you could also split your set into this way and still do branch and bound. And actually, you could even be more general. So you could take any kind of disjunction. So for instance, you could decide that your initial set is also split into this part, maybe this part, then maybe, I don't know, this part and this part. It's still a disjunction into 4 pieces that covers these 4 pieces cover the integer point, so it's still fine. In some situations where the branch and bound is not the standard branch and bound, but a branch and bound based on the specific combinatorial optimization problem you have at hand, that sometimes it is convenient to work also with the more general disjunction. So we consider all possible disjunction, but just keep in mind the case of split disjunction for this talk. Now, once the notion of disjunction is clear, at least a split disjunction, then we can just recall branch and bound like cutting plane, because it's useful to recall them. So branch and bound, it means that you have your relaxation, you select that disjunction, for instance, okay, actually first you optimize and you find the optimal solution, then you select the disjunction, and let's say this may not be a variable disjunction, but it could be a variable disjunction or a split, so a skew disjunction. And then you optimize over the two sets. In our study, to simplify things, we assume to always use the best node strategy when selecting the next node to process in the branch and bound tree. So we always take the node which has the most promising linear programming value, or at least the continuous relaxation, value of the continuous relaxation, because this simplifies the analysis, because then you know that the first feasible solution that you find is also an optimal solution if you use the best node strategy. And then if we look at cutting planes, well, we will restrict to split cuts, because split cuts also arise from disjunction. So this allows us to make a sort of a fair comparison between branch and bound and cutting plane. So specifically, you have your polyhedron or continuous convex set C or P, sorry. You find the optimal solution. You again apply a disjunction, but this time you don't go over optimizing over the two sets, but you introduce any valid inequality with the requirement that it is valid for the two sides of the disjunction that you have created. Okay, so this is a valid inequality, and when it arises in this way, it's called a split cut. Actually, it's called a disjunctive cut if you're working on an arbitrary disjunction, but if your disjunction is a split disjunction like in this picture, then this is called a split cut, and this is what we will going to consider. Okay, so in this sense, when you take disjunctions, you can do branch and bound on using those disjunctions, or split inequalities, split cuts using those disjunctions. So you can, I mean, in a sense, fairly compare the two algorithms. Now, how do we compare the, okay, forgetting to say that, then what you do is to add this inequality to your linear relaxation. And so you So you have this inequality value for the two sides, and then you take the new polyhedron or continuous set, convex set that you get by adding the blue inequality to the original set. And then you go over and optimize over this single set. So you don't create two sets over which you want to optimize, but just a single one. Now, to compare these two algorithms, so we know that branch and bound is represented by a tree called the branch and bound tree, in which every node, at least except for the leaves, every node has two children in the standard branch and bound, or at least two children if you use a more complex disjunction. Also, cutting plane can be modeled with a very special tree, which is just a chain. So you can take the root node that given relaxation, then you apply a cut, you get a smaller set, then a smaller set, and you can depict this with a very, very degenerate tree, which is just a chain path. This is useful because then you can say that also branch and cut can be depicted by means of a tree. In this tree, you have some nodes that have more than one child. These are the branching node where you have done some branching, and other nodes that are just cutting nodes where you add a cut. So for instance, you could start from the root and apply a couple of cuts, then you could do branching, then maybe you do another round of cut and then again branching. You can create a tree like this, which represents the branch and cut algorithm. We do this because then we can say that if we want to compare the time that one algorithm takes with respect to the other, well, you can just count the number of nodes, because the number of nodes that we create in the tree is just the number of linear relaxation that you have to solve. And in a sense, this is a very rough measure of the complexity of the algorithm. So what we compare is the number of nodes that we produce in this tree, and this is called the length of the algorithm, because this really counts the number of linear relaxation, and solving the linear relaxation is usually the most the heaviest step in these algorithms. Of course, this is very just a rough approximation. We have also some results in which we also take into account the sparsity of the constraints that are introduced during branch and bound cutting planes, because a larger linear program could be easier to solve if the constraints are very sparse. So it's really an approximation, but let's work with this simple approximation. And then we also assume that the tree that we produce are the optimal ones. Okay, so we assume that we are so smart that we can have the optimal branch and bound, the optimal cutting plane, and the optimal branch and cut tree for the problem we have we are considering. Okay, before starting to see some results, let me point out that there is a very important difference between algorithms and proofs. So usually we are talking now about, we're talking of a cutting plane, branch and bound, and branch and cut algorithm. So algorithm is the term we use when we impose that the cut, for instance, that the inequality that we introduce in the cutting plane algorithm must cut off the current solution. But in principle, one could also think of using any disjunction, even if it doesn't cut off the optimal solution. So what I mean is that I have my polyhedron, this is my optimal solution. I could also introduce this disjunction and then create this cut. This doesn't cut off the optimal solution, but it could be useful later in the algorithm. This is not an algorithm, it's not a cutting plane algorithm because it doesn't cut off the optimal solution. It's called a cutting plane proof in this case. This is the name that the literature reserves for this. And you could do the same also for branch and bound and branch and cut. You can think of the branch and cut algorithm in which you are not required to cut off always the optimal solution. Maybe you keep it and you do something in another part of your feasible region, which will turn out to be useful later in the algorithm. And indeed, it's clear that every, let's say, cutting plane algorithm is also a cutting plane proof, because a proof is the requirement to be a proof is weaker. You don't need to cut off the optimal solution. But there are examples, even in dimension 2, which show that proofs are really something, they are really stronger than algorithms. So there are examples in which you can easily solve a problem if you use a proof, so you are not forced to cut off the optimal solution, but if you are forced to do that, then it will take much more time. Now, in the results that we will see, I mean, some of them works for algorithms, some of them works for proofs, some of them works for both of them. So I will not always be precise because otherwise it becomes too technical, but let's keep in mind, I will usually speak of proofs, cutting plane, branch and bound and branch and cut proofs, but most of the results also work for the algorithms, for the algorithms. That is an important distinction. Okay. Goal number 1, compare branch and bound and cutting plane. I want to fill in as much as possible this table. So in this table, there is a first distinction. You see two rows, because I am distinguishing the case of a fixed dimension, which means that we treat the dimension as a constant, and the case of variable dimension. So now please don't get confused. Here, variable just means not fixed. It's an adjective, while here variable has another meaning, means disjunction based on a single variable xi. So maybe the wording is not really the best one, but so variable dimension means that the dimension is not fixed, it's part of the input. Fixed dimension means the dimension is a constant. Why am I doing this distinction? Because, for instance, in integer programming, it's very well known that integer programming is NP hard, but if you fix the dimension, it becomes polynomially solvable. So since there is this very clear distinction between fixed and non-fixed dimension, let's also study these two settings separately. Then I make a distinction between a variable and split disjunction. So as I said, variable disjunction means xi smaller than or greater than some number. Split disjunction is more general, is something which is not necessarily given by a single variable. It's something more general, just any split disjunction, any skew pair of hyperplanes will work. And for each of these two cases, there is a distinction between 0-1 sets and general sets. General sets means general convex sets. Why? Well, I think it's clear. 0-1 sets are very, very special and very, very common. So maybe it is worth looking at them separately. So the first thing we can observe, this is trivial, but just to start to fill this table, is that in fixed dimension, branch and bound runs in constant time, just because in fixed dimension, in the 0-1 case, sorry, in the 0-1 case, because you have just a constant number of 0-1 points. So in fixed dimension, the number of feasible points of a 0-1 problem is constant. So in branch and bound, in the worst case, you will enumerate all of these points when you do branching, variable branching, which means xi equal to 0 or xi equal to 1. So sooner or later, in constant time, you enumerate all possible feasible solutions. So branch and bound runs in constant time. This is trivial. And a little bit less trivial, but one can work out the proof that also the cutting plane approach based on variable disjunction, so when the disjunction are just on a single variable, also runs in constant time. So this is not so trivial, but let's forget about this case. Let's go to the case of 0-1 set, but yeah, first let me observe that, of course, if what I said is true for a variable disjunction, then it is even more true, let me say, for general split disjunction, because you have more disjunction to use. So this is also an immediate consequence. First non-trivial result is this one. So in the 0-1 setting, this notation means that if you have a branch and bound proof of algorithm, let's say proof of some length, then you also have a cutting plane proof of the same length. So in a sense, in the 0-1 setting with variable disjunction, cutting plane dominates branch and bound, which might be a little bit surprising, of course, from the theoretical point of view. Actually, this result is due to dash, implicitly Schwatal, but let's say it's due to dash. And let me mention the proof because it's interesting. I will only mention a couple of proofs. So the result is that if you take a polytope, so dash only prove this for polytopes. Then we have an extension for convex sets. So if you have a polytope and in the 0, 1 cube, and the proof that an inequality is valid by means of a branch and bound, or even a branch and cut, even more than that, even a branch and cut algorithm or proof of length n, then you can find a proof of the same length with which only use cutting planes. So you can just use cutting planes. You don't need to branch. This is the point. What does this mean? So, and how do you prove that? Well, first, let me clarify what I mean that an inequality as a proof. It means that when you create your branch and cut tree, all the leaf satisfied, let's say that the inequality is Cx less than or equal than delta. It means that all the leaf corresponds to subsets, to subproblems that satisfy the inequality. Okay, maybe you want to prove the optimality, so this could be the inequality that says that the optimal value is at most the optimal value, that the objective function is at most the optimal value. Maybe you're proving the optimality or just the validity of an inequality. So this means that all the leaves satisfy the inequality. Now the proof is the following, more or less. So first you can assume that there is at some point a branching node, because if you only have cutting nodes, then you already have a cutting plane proof. So at some point you have a node which is a branching node. And let's take a maximal depth branching node, meaning that all the subsequent nodes are just cutting nodes. So there is no branching anymore. And let's call Q the relaxation corresponding to this node. Here I am applying a disjunction xi equal to 0 or xi equal to 1. And so I create a set that I call Q0 and a set that I call Q1. Okay, this is branching. And since we are in the 0, 1 cube, when you impose in the equations xi equal to 0 or 1, you actually are creating phases of Q. So Q0 and Q1 are phases of Q, and this is crucial. Now, if you look at this sequence of nodes, these are cuts, split cuts based on variable disjunction. Okay, and these give a cutting plane. This is just a cutting plane proof that, so if you look at these two leaves, you know that the inequality C transpose X less than or equal to delta, which is the inequality I want to prove, this is valid for them. Just because we have a cutting plane, a branch and cut proof which terminates with these leaves. Now, the point is that what is this node? Here you are considering the disjunction xj for some j equal to 0 or 1, but you are not doing branching. You are using it to create a split cut. Now, this split cut that you create here is valid only for Q0 and not for Q, But it turns out that by doing some rotation of this inequality, you really rotate geometrically the inequality, you can have this, not this cut, but you can modify this cut. So you do a little bit of modification and you get an inequality which is valid for Q with the following property, that this new cut, okay, first it will be valid for Q, but it will still be a split cut coming from the disjunction of on xj. So it's still a split cut, and the effect on Q0 is the same as before. So this rotation is such that you don't change what happens on the hyperplane xi equal to 0. So the effect on Q0 is the same as before. Now, if you have these properties, what you can do is the following. It's very simple now. You can just say, okay, I start from Q, and then I don't apply exactly this node, this cut, but I apply the modified cut that I have just described. And then I do the same for the following part, for the following cuts. And then I look at these cuts and I do exactly the same, but instead of appending these cuts to Q, applying this cut to Q, I can apply them here. Because this is a smaller set than Q. So if I apply cuts to a smaller set, then it's even better, right? Now, starting from Q, I have created a cutting plane, a sequence of cutting planes, and let's call this last node let's say it's a set, it's a relaxation called R. If you look at the two faces, R0 and R1, created by xi equal to 0 and xi equal to 1, well, they are a subset of these nodes. R0 is a subset of this, and R1 is a subset of this, because I have applied the same cuts. But we know that this inequality is valid for these two nodes, so it's also valid for R0 and R1. So what I'm saying, this is the last step, is that Cx less than delta is valid for R0 and R1, which means precisely that it is a split cut, i.e. it is a split cut for R. And so that means I can append, I don't have space here, but I can append a last node here, which is just the split disjunction applied to xi equal to R0, xi equal to 1, to show that this inequality is valid for R0 or R1. And so I have eliminated one branching node. Then you iterate this and you eliminate all the branching nodes without changing the number of nodes. Okay, I don't know if this was completely clear, but let's just remember that in a sense you just take this final pass that you have after the branching and you concatenate them by changing a little bit the cut with some lifting, and then you only need one extra node to conclude. Now, our first result is that this can be extended to the convex case. So the statement is exactly as above, but now the set in the 0, 1 cube is convex. But now we are only able to prove that the inequality, okay, I called it delta before, that the inequality is valid up to some epsilon. So for any epsilon, if we have a branch and cut proof of length n of our inequality, then we have a cutting plane proof of the same length, which only use cutting planes, which prove the approximate inequality Cx less than equal than delta plus epsilon. And the surprising things to me is that you can make epsilon as small as you want, and you will never increase. You can still keep n. You don't increase the length of the cutting plane proof, but you cannot set epsilon equal to 0. At least not with our proof. So the lifting up the rotation doesn't work. This is the problem. So this is very surprising to me. So epsilon can be made smaller and smaller. This is okay, but without having n increasing. This is strange, because then you would expect to be able to set equal to 0, but this is not the case. And indeed, our first question is whether this epsilon can be set to 0. Anyway, let's go back to the table. So in the 0, 1 setting, if you use a variable disjunction, cutting plane is is better in principle than branch and bound. And there are examples in which it is really better. So we can construct an example in which of a 0, 1 set in which the cutting plane approach based on variable disjunction take a polynomial time, n is the dimension, the number of variables. While the best branch and bound you can do there, based on variable disjunction, will take exponential time. I think I will skip the description of the example, but it's just an instance of the stable set problem, or the common relaxation of the stable set problem, in which you take n disjoint copies of the triangle. Then you can solve the problem with the 3 iteration per triangle with cutting planes, but you need roughly 2 to the n nodes of the branch and bound tree to solve the problem if you use branch and bound. This is a very pathological example, because when stable set is made on disjoint graphs, you can solve, of course, the problem into each single component, but you can make the example less pathological by connecting these triangles in some way. So there are also less pathological examples. Now, if we have this example in the 0, 1 case, well, this is also an example that works in the case of general sets. Of course, when I have a counterexample an example in the 0, 1 case, it can also be seen as an example of a general set. So also in general, with variable disjunction, but for general sets, cutting plane can be much better than branch and bound. Is it still true that cutting plane is always better than branch and bound? Well, the answer is no. Actually, there are also examples, if you go to general sets, in which a branch and bound is extremely better than cutting plane. So when you move away from the 0, 1 settings, this sort of dominance that the cutting plane has with respect to branch and bound completely disappears. You can have example of both types. One can dominate the other. This is an example actually which lives in dimension 2. Again, I will not describe it, but it's a very simple two-dimensional examples. It's a quadrilateral in which you solve it with branch and bound with variable disjunction in just 4 iterations. But if you try to do cutting plane, unfortunately, you will only converge. So if you only use variable disjunction, okay, if you use a general cutting planes, general split cut, you will converge, but with only variable disjunction, you will never converge in finite time. Okay, so this is a very simple example. And so you see a very big difference, sharp difference between the 0, 1 setting and the general case. Now, as I said, this example is in dimension 2, so I can also write it here. It's an example also in fixed dimension. So I can also write that this example works for fixed dimension. So the next question is what should I write here? So do I also have an example in which the cutting plane approach is better than branch and bound, or branch and bound is always better than cutting plane? Well, the answer is that branch and bound is always not too, I mean, can be worse than cutting plane, but not so much. So branch and bound is always bounded by a polynomial in the cutting plane length. I mean that if there is a cutting plane proof of length, I don't know, n, then you have a branch and bound proof or algorithm of length n to the n, where n is the dimension. But the dimension is fixed, so this becomes a polynomial in the cutting plane length. So this is why I write this notation. And actually, this is a result that I will skip for one specific reason, but it is very, very general. So it doesn't work only when you have a variable disjunction. This is true whatever kind of disjunction you decide to use, provided that you use the same kind of disjunction for both the branch and bound and the cutting plane approach. So these results could be written also here and in many other places, but I will not write it also in other places. In this situation, for instance, one can say something better. Okay. So essentially, the proof of this result is that you can take the cutting plane proof and mimic it with the branch and bound tree. And you can do it always, but in this special setting, you get this result, which is the best one you can get. Here, you will get the same result, but you can get something better, because when you use all the split disjunction and not just the variable disjunction, you have this very interesting result. So branch and bound is always better up to a factor of 3 than cutting plane, which completely reverse this inequality. When you go to variable disjunction to split disjunction, you completely reverse the dominance relation between branch and bound and cutting plane. This is the last thing I want to prove, because it's very, very simple. This is really simple, much simpler than the previous proof. This is simple. You can prove it this way. So the result works for any convex set. We don't use polyhedrality. So suppose there is a valid inequality which is which has a cutting plane proof of length n using general split disjunction. Then you can construct a branch and bound proof of length 3n. Why? Well, you just do the following. Let's say this is our convex set C. And let's say that you start, so we have the root node C, and now you apply some disjunction. So this is, I don't know, AX less than or equal than beta, and this is AX greater than beta plus 1. So this is my disjunction. I have a cutting plane proof, so the first thing that I have at the root node is a cut. I have some cut like this, Cx less than or equal than delta. Okay. So this is the first thing you do, and this create a new set in which you add this inequality, which is a subset of C. Now I want to construct a branch and bound proof. What do I do? Well, I don't apply this disjunction, but another one. I will impose either C transpose X less than or equal than delta. So I take this, assuming that every number is integer in this notation, C and delta are integer vectors and number, or this one, which is this one. This is a C transpose X greater than delta plus 1. Now, if you look at the node that you create here, well, it corresponds to this set, which has no intersection with the left part and the right part of the disjunction based on A. So I'm saying that if you here apply the original disjunction A transpose X less than beta or greater than beta plus 1, you get empty nodes. Okay, you can see it from the picture, but it's very easy to see. So the tree terminates there, and what you get here? What you get here is exactly this set, which is exactly the, let's say, C prime. It's exactly the second set you get when you apply the cutting plane proof. It's just the original set plus your cut. So now here you can replicate the argument because this is really the second node of the cutting plane proof. And again, here you will get, so this is what we got so far. This is C, this is C prime, and then you get again C double prime, and here you get something like this with the same argument. And then you continue. So you are just multiplying by three the number of nodes. Okay. And okay, this can be extended, but let's keep this. And then you can also answer the question, okay, is there an example in which branch and bound is really faster, I mean, much faster than cutting plane, or could also be, yeah, or maybe they are just very close to each other. Well, the answer is that, yes, there is an example in which you have a sharp difference, okay? Branch and bound can take constant time, even in fixed dimension. This is why I'm writing it also here. Branch and bound can take constant number of iterations, and cutting plane can take a number of iterations which is polynomial, not exponential, but polynomial. I don't know if exponential, that's a question actually. So I will skip this, but let's keep this description. The only thing we cannot fill in is the only part is this one. We don't know whether with the split disjunction on 0-1 sets, there is an example in which branch and bound is really, really better than cutting plane. This we don't know. This is the open question that remains in this table. Okay, now let me go. This will be really a matter of 5 minutes to the second question, because I cannot spend too much. I cannot give too much detail about this, but when is branch and cut really superior to just branch and bound and just cutting plane taken alone? So this table suggests that many times there's no superiority of branch and cut on branch and bound and cutting plane, because take for instance this situation. Sorry, this situation. Since cutting plane is better than branch and bound, if you do branch and cut, the branching part can be described as a cutting plane algorithm. So branching doesn't give much more from the theoretical point of view with respect to cutting plane. So branch and cut can be replaced by just cutting planes. Vice versa in this situation or this, branch and cut can be replaced by just branching. You only lose a factor of 3 in the cutting part of your algorithm. So there are many situations in which you see it doesn't pay off to use branch and cut. I repeat, from a theoretical point of view. So the intuition is that we are considering this study situations in which the branching and the cuts come from a similar paradigm, which is that of disjunction. So they do similar things. So maybe this is the reason why there's no superiority of branch and cut with respect to just branching and just cutting. So we make this definition. We decide that a branching scheme and a cutting plane paradigm. Now, this is not necessarily split cuts. Now you can take any cutting plane paradigm. We call them complementary if you can find a family of instances where CP cutting plane is exponentially better than branch and bound, and another family of instances where branch and bound is exponentially better than cutting planes. So if your paradigms are such that you have instances of both type, then we call the schemes complementary. So for instance, this is the situation we have here. Sometimes branch and bound is much better than cutting plane, exponentially, even infinitely better. Other times, branch and bound, cutting plane is exponentially better than branch and bound. This is a complementary. In this situation, this is a complementary pair. Well, what we can prove, or another example is branch and bound based on variable disjunctions, which is the standard branch and bound, compared to Schwarzschild cuts. It's there are in the literature you can find families of both types in which branch and bound exponentially beats Schwarzschild cuts and vice versa. Our result is that under the assumption of complementarity, indeed you can prove that branch and cut is exponentially better than branch and bound and cutting plane. So in a sense, what happens is that if you use branch and cut, you can solve you can construct instances which are obtained by pairing somehow the two families of instances, in which if you run branch and bound, it will take exponential time. If you run cutting plane, it will take exponential time. But if you run branch and cut, it will take polynomial time. Okay, in the dimension. This is a very informal statement because there are some mild assumptions are missing from this statement, that they are really, really mild assumptions that are always satisfied from by all the branching and cutting scheme known in the literature. So the idea is that if branching and cutting do really different things, meaning that there are instances where one beats the other and vice versa, then branch and cut is superior. There are some open questions. Let me just pose the first one because I am running out of time, but at least the first one is whether the previous theorem can be reversed. So I said branch and cut is superior when the pair of schemes is complementary. Is this the only situation when branch and cut is superior? So can one prove that if there are instances in which branch and cut exponentially beat the branch and bounded cutting planes, then branch and bounded cutting planes are complementary to each other? We don't know the answer. We have some partial answers, but not satisfactory answers. Then I think I will skip the other questions because are a little bit less related to this topic. They are related, but not as much as the first question. So I think I can stop here. Thanks for your attention.
Thank you for this very nice and clear presentation. One last time, if anyone has questions, it can be asked in the chat or by raising your hand. And since I don't see any, I have a first question. In the first proof that you presented, you have a branching node Q that leads to Q0 and Q1. And you said that the first cut applied in Q0 is not valid for Q. I don't see why it is the case. Could you elaborate?
Yes, I can. Let me re-share just a PDF. Okay, I will use this blank space to write. The point is that so you are doing branching here, okay, based on xi equal to 0 or 1, and then you have a sequence of so this is what you have as input. Okay, you have a cutting plane, sorry, a branch and cut proof, which I mean it's much larger at some. So this is really branch and cut. So you branch and you create two subproblems. this means that you are applying a cut to Q0. It's really the meaning of the branch and cut tree. So if I do this, this means that this is a cut for Q0. So an equal. So here, when you create the cut, you are only taking care of Q0. There's no reason why this cut should be also valid for Q.
Okay, but it could
it says branch and cut, right? So if you cut at the root node, of course, you have something valid for Q, assuming Q is the root. But if you cut at the child node, you're only taking cuts valid for that child.
Okay, so
does this answer your question?
Nothing guarantees. It means that nothing guarantees that it's valid for Q, but it could be, or I missed something.
Yeah, it could be. Of course, it could be. But I need to be sure that I have a cut valid for Q, because then I want to replace this this tree with just a chain. And if I want a chain, then this has to be valid for Q. This has to be valid for the predecessor, and so forth. So I need to modify this cut a little bit, and this is done by this rotation argument, which is which I didn't present precisely because it's a little bit technical, but it's just a rotation argument.
Okay. So does in the case where the cutting plane can be better than the branch and bound, does it mean that to solve this kind of problems we should try to find better separation algorithms, or in practice it's not necessarily efficient?
Yeah, I think there is a difference between a theory and practice. So I don't know. I mean, it could be an indication that. So I mean, I think it's common knowledge that cutting plane alone, maybe branching alone does something. Cutting plane alone usually are not very efficient. Maybe it's an indication that yes, I mean some effort to find good cuts could be worthwhile, but I wouldn't take these results as just like really as this is not really the truth from the practical point of view. Of course, it's just a theoretical study. Yeah, but sometimes it's nice to see at least if the theory matched the practice or not, and this was our attempt. Yeah.
Okay, thank you very much. Again, this was really a nice and very clear presentation of a technical topic. So thank you a lot about that. And since I don't see any raised hand, I think we will close this presentation. Thank you again, Marco.
Thank you.
So